Hello and welcome to video number 2 in the UMMZ CT data and segmentation tutorial series. Again, my name is Ramon Nagesan. I am the CT lab manager from the University of Michigan Museum of Zoology. And today we're going to be talking about CT data. We're going to do a short introduction to what CT data is. This video will only be about 4 or 5 minutes long. We're not really going to go into any segmentation or anything like that. We're just going to talk about some files. So just as a quick reminder, these videos are being produced from the University of Michigan Museum of Zoology. If you would like to learn more about our museum, please go to the website that you can see on screen right now. You can learn all about our collections, the people who work there, and some of the research that comes out of our museum. So, like I mentioned, this is going to be a quick introduction to CT data. We're going to talk about really quickly how CT data are created, and then, of course, what are the file types that you can expect to have when you do a CT scan. And then we're also going to talk a little bit about how the CT data is organized. So again, we have at the University of Michigan Museum of Zoology a Nikon micro CT scanner. This machine is adequate for scanning anything that can just about fit into a 5-gallon bucket. So we have scanned some relatively large specimens, some large boid snakes, as well as a vulture. So we can get quite a bit of variety and diversity of organism into our CT scanner to produce data like you see on the right of the screen, those 2 examples that I showed in the previous video. So for these video series, I'm not going to get into too many of the technical details about CT scanning, at least perhaps in this video. But just as a reminder, I want to talk a little bit about how the data is produced. So in the top left-hand corner, you can see a diagram of the CT scanning process. So we have a specimen on a rotating platform, in this case shown as the bird. We have an X-ray gun, and then the red beam you can see is the cone beam. So our particular scanner produces a cone beam of X-ray radiation. The data from the specimen is detected on the detector panel as the attenuations of the X-rays as they pass through the specimen. That information is then compiled into a series of projections, which you can see in the bottom left-hand corner. So these projections are akin to the radiographs that you might see at a doctor's office when you get an X-ray of, say, a broken bone or something. And then we do a reconstruction of those projections into what you can see on the top right-hand corner, which are our tip stack, which these include cross sections of the specimen. So you can essentially look at the bones in a variety of anatomical views, or whatever structure, doesn't necessarily have to be bone there. And those are usually produced as TIFFs. Those data can then be taken and compiled into 3D models, like what you see below. So from here, I'm actually going to show you what the data is going to look like, as in what the file structures are going to look like. So here we can see I've opened just an Explore window, so I'm using Windows. This might be a tiny bit different on a Mac, but not that much. If you get a data set from us at the UMMZ, what you will see in the main folder name is firstly the Darwin core triplicate, so the university institution name, so in our case UMMZ, and then the collections code. So in this particular data set's case, it is mammals. We have the specimen identification number, and then the species and genus. Now, in some cases, we will have additional information. For example, if I scan a male or a female, I may have an M or an F following the species and genus. We may also have the word skull or full body, or even DICE CT in the event that the scan is a DICE CT scan. So we're just going to click on this data set. Here you can see when you open it, you have a number of things that will pop up at you. Firstly, the first thing that you might notice are these projections. So in this case, there are 600 there should be 1,601 projections, which is based on some of the parameters that you would have entered when you ran the scan. There are a bunch of metadata files here, as well as a reconstruction. And we're going to get to the reconstruction afterwards. And then there's some information in the center slice. So I'm only going to be talking about the things that you will need and things that you may want to know a little bit more about. So as you can see, these are the projections. If I were to double click on them, or at least one of them, in this case, I already have one open, here we can see just a 2D image of the specimen that was scanned. As we scroll through these, it'll be kind of hard to see, but the specimen is now rotating. So there is an image there are 1,601 images through a 360-degree turn of this specimen. So that is essentially what these projections are. And they are generally TIFF stats, or TIFF files rather. The next file that you're going to need from here is this file right here. In our case, it's an XTech file. Now, if you're using a different brand of scanner, this will have a different file extension. These XTech files or these information files generally are proprietary to the machine that you create your scan on. Now, generally speaking, if you do a scan on any machine, you will have a file of some kind like this that encodes your scanning parameters. So if we double click on that, we can open it up as a notepad file. In this case, I'm using Notepad++. But what you really want to see here, the most important piece of information, are the voxel sizes. Now, the voxel size represents your scanning resolution. So if you want to ever open up these data in a segmentation program or something like that, you will need to know the voxel size. So here, what we can see is voxel size X, voxel size Y, and voxel size Z. Now, in the case of our scanner, X, Y, and Z are always going to be the same, and that will be the case for most scans. And you see this number, it's 0.04055.294. So that is the size of your voxel, or your pixel effectively, for your scan. It's your resolution. And in our file output, this is in millimeters. And the reason this matters is when you go to import your data into a segmentation program, you will probably be asked to import this information as well. Now, there are some other information that can be important potentially to you, perhaps when you get to writing your paper, available in this file. I'm just searching for it right now. For example, it does encode the name of the specimen that you're working with, as well as the kilovolts that the specimen was scanned at, in this case 85, and the microamps that the specimen was scanned at. Now, generally, when you're writing a paper, you will want to report the power parameters for your scan, as well as these resolution parameters. All right. So going back to our file tree, the next place that we want to take a look is into our reconstructed data set. Now, you cannot use these projections for creating a segmentation, but you can use these, you will be using these reconstructed data for that purpose. Again, we have another XTech file here, which encodes that same information that I just showed you. But now you can see the TIFF stack that is shown actually is no longer the projections, but instead are a series of cross sections. As you can see going along, these are sequential slices through the specimen, generally from top to bottom, however that may be oriented in a particular scan. And what these data look like when opened is this. So here what we can see is a slice through our specimen. In this case, it's a bat. And we have a few structures that are visible. These are part of the limbs, likely the wing. And here we have likely parts of the vertebral column. And as we click through these files, you can see that morphology slightly change again. Now, it's when this data set is compiled in a segmentation program, be it Volume Graphics, Dragonfly, or a Episdoe that you are able to get a 3D model. Now, if you're working with a scan that we have produced at the UMMZ, you will automatically get a volume graphics project file. Now, all you need to do to look at this in 3D is double click on this particular file and it will open volume graphics. Now, that is in the event that you have volume graphics on the computer that you're working on. At the UMMZ, all of our computers are equipped with that, so you can just double click and open it here. But say you wanted to work in Dragonfly or Episdoe, or even manually enter this data, open these data in volume graphics, you would be working with these files right here. So that's it for today's video. The next video is going to probably cover Morphosource and more about our archiving and data uploads. So please keep an eye out for that. Today, if you have any questions, please feel free to send me an email at Ramon or at rnagesan@umich.edu. Thank you.